All right. Good morning, everyone, or afternoon if you're on the Northeast Coast time. Welcome to Understanding National Electric Code. Uh, this course is going to be a slog. It's intended as a 6-hour kind of start to finish review of National Electric Code. We're going to focus on solar power, batteries, and generators with respect to building electrical systems. We need to be familiar with how all of our on-site distributed power resources interact at the electric service panel and the point of interconnection. But if you're like me, you got into solar because you wanted to be near solar technology, or you might be a building designer who puts solar into building specs, but you might write in install per NEC or install per code. And with technology creeping further up into building design in terms of enabling the advantages of the smart grid, you might want to learn more about electrical system design of the building, or you might be a solar installer who's trained up on section 690, the solar section of code, but you've never gotten around to the other sections of code in terms of actually reading them. And if you actually go into the early sections of National Electric Code, you'll see that it forms the fundamentals that drive the later sections in code. So maybe in your career, you've proceeded on just brute memorization of National Electric Code, which can be very important when you're in the field. But what we're trying to do today in the context of continuing education is to kind of expand our comprehension of code, on why certain code requirements exist so that we can become more accurate when we encounter those unknowns in our electrical design or out on the job site, particularly if you're handling multiple trades. So I will find myself commonly as a system designer. My thing is I try to enable mainstream contractors to do work. And so I might get an electrician who knows actually more than me about like the section 200 or 300, where I'll pick up on things like the conduit, the junction box sizing from a general contractor. But then they'll just look at me and for the life of them not be able to fully understand what's going on with a solar array one-line diagram, because they almost seize up when they get into DC electronics, and they say, well, I know how this works on AC, but on DC there's no neutral line. Or maybe it shows there's a neutral line being used for communication, but not as a neutral would be used on an AC system. And they just say, I don't know what to do, so they stay out of it. You might be the point man on the project side where you have to coordinate multiple trades, and knowing code is how you're able to talk to all parties in a confident, competent manner. So most of our course content today is going to draw from the first 4 sections of National Electric Code, which govern general practices, and then we'll spend some time on specialty equipment, battery banks, more tomorrow. Of course, we might find that the early sections are so boring that we have to take a break and look at some solar code reports just to shake up the monotony. The program in general will have a solar flavor to it because I'm a solar designer, but it should also serve as a good basic introduction to code. In general, if you're an architect or an engineer and you don't care about solar power for some reason, you still should get some value out of this program. And we want to do this because, as we talk about in other courses, the soft cost in solar is very high, and that's because we have this concept in the industry where you need a specialty contractor to execute a project. And in competitive solar markets, the specialty contractor can be competitively priced. But if you're in the middle of the United States, that specialty contractor may be priced so high that the projects are not economic, and we're kind of interested in where the economic applications of solar can come out of the ground. So, I think there's opportunity for both quality improvements and cost savings in this industry. The general contractor, just keep in mind that the general contractor will know a lot more about the first 4 sections of code, but might be deathly afraid of the later sections of code regarding specialty equipment. And then there's room for a specialist on a job site who knows, I love being the guy who can just show up and coordinate the solar stuff and just let the electrician do the rest of the project work. And if we streamline all those efforts together, we can actually grow this industry, let the solar guys do the solar stuff, but bring other trades into the industry to reduce project cost as well. So one difficulty in teaching National Electric Code is that we're not allowed to simply print out the code book and give it to you as a handout, and that can make it difficult as an instructor. But also, code in general is intended to be referenced only, so not, it is subject to copyright. The guys who make code will make money off selling the code, and that revenue goes to maintain the quality and the administration of National Electric Code. What's surprising about code is it's not a public resource. So you have all these governmental agencies saying you need to install per National Electric Code, but it's not a public resource. It's run and maintained by a private organization. Now, they have a very altruistic goal, but the way they keep the wheels turning is by selling code books. So we can't just print out code and give it to you in a handout, and that might make things a little bit difficult in terms of creating course slides, but we'll see how it goes. So when you see code up on screen, what I've tried to do is abridge it or kind of pick out the important parts of it. But to get into the actual code, you actually have to go out and buy a code book. Let's see. Now, all of the National Electric Code, the official books, the one thing I have to say is they are actually of exceptional quality. So I'm not a guy who can really take care of nice things. And I recently bought a copy of the National Electric Code 2017 for this class. My old code book was NEC 2011. I was actually able to sell it on eBay. And I run through my objects pretty quickly. In a code book, you're putting that in your work truck, taking it out with you, using it a lot. But it held together, and it's still, an old copy of code. If you're budget constrained, you go out and buy NEC 2011, and it's not like there isn't useful information in an older code book. In fact, the older your code book, the more simple the code is. And so if you're just trying to learn code, buying a used, outdated copy of National Electric Code is not a bad idea. Although I do like the changes that they've made to NEC 2014, or rather NEC 2017. The code sections and the battery sections of code are just being established. And so safety provisions are just being written into code for the first time. 2017 has clarified ambiguities in 2014, but there really isn't a lot of new stuff in terms of what a solar designer needs to be aware of. Rapid shutdown is still there. The main thing the main concern about NEC 2017 was that they were going to require rapid shutdown, not just at the array itself, which is a good idea, but to take rapid shutdown a step further and require every single module on the rooftop to turn off during a rapid shutdown situation, so that the power didn't just stop at the array where you still have higher voltage, but that they were going to take it one step further and basically require microinverters or something like that as part of code. And the code did not do that. So the NEC 2017 expansions are all more clarifications rather than putting in new requirements into at least rooftop kind of residential and commercial solar design. Okay, so let's see here. So one thing we have to do is that, so a couple more kind of motivational snippets, and then we'll get into the course content itself. You know, if you become an expert of code, you can always stay a little bit ahead of the automated design software. You'll often find, you know, you're in a good place in the industry if you're using solar design software and you realize, well, the software doesn't exactly have what you're doing, because that means you're on the frontier and you're kind of a specialist and you can take on specialty projects and stay relevant. You know, otherwise, basic solar design is getting fairly automated, as we see in other classes. And scroll down a little bit more here. Okay, so let's see. So I guess the last thing we have to do is disclaim liability. So code is a minimum level of safety. In fact, you're going to find situations where you say, well, you know, I might be in a dry environment, but this room could get some water into it if there's a hole in the attic or something. So I want to design it like it's a wet environment as well. You know, you can do that. You can go beyond the minimum standards of code, and electricians do it all the time in terms of upsizing their conduit, upsizing their cable. Given that it's a private organization maintaining a private code that's you know, intended to be referenced only, we also have to disclaim liability to the NFPA for teaching this program. You know, this program is not, just like code is not intended to be a manual for do-it-yourselfers to overcome their lack of knowledge and cut out a licensed, competent person from executing electrical scope. Teaching this class is not a substitute for using licensed electricians on the job site. All right, so that's a lot of rigmarole. Let's get into actual course content. We're going to spare you with going through a lot of definitions. You know, what we're going to do is skip over the definitions and just bring up the definitions of the terms as we get into them. So why don't we start out with deteriorating agents. You know, no conductors or equipment shall be located in damp or wet locations exposed to gases that have a deteriorating effect or excessive temperatures unless identified for that purpose. So solar arrays and generators are usually located outdoors, and that means they're exposed to the elements. You know, if they are protected, you know, a generator might be kind of housed in an awning or something like that. You know, if they're sheltered and not subject to direct water spray like rainfall, you know, that would be a damp location. So a solar array, you know, you might look at it on the roof and say, well, it's normally dry, but if it rains, is that a damp location or is it a wet location? A damp location might be in an outdoor environment where the equipment is not subject to direct water spray. So if you have a screened-in porch, and your inverter is in the screen and porch, that's a damp location. But your rooftop is actually a wet location, and so all the wiring and fittings and conduit that you're using up on the rooftop need to be listed for wet locations, even if they're on the rooftop. Now the rooftop is a wet location, but it's also subject to extreme temperature. And so we're going to get into temperature ratings in the program, and there's going to be wires listed for 75 C temperature and 90 C temperature. You might ask yourself, well, okay, I'm using wire, and I'm using a 75 C temperature calculation, and my wire is well sized, and I have the amperage in it, so it's well sized. Do I need to be using 90 C wire if my 75 C wire has sufficient amperage? Well, just, rather than getting too caught up into the technical side of it, if we take a step back and we say, okay, the rooftop is subject to extreme temperature. Out of every place on your building, the rooftop's going to be one of the hottest places. So should we be using wire that is rated for a higher 90 C environment on your rooftop? Yes, it's one of the hottest parts of the building. If you have the opportunity to use a better fit piece of material for that rooftop, then that's great. You want to use the 90 C wires on the rooftop. Even if you end up doing 75 C calculations, just keep in mind that if you're trying to optimize your cost by designing all the way up to the, what is the cheapest wire you can possibly select for the job, that is a path towards mistakes. It's better to over-engineer and think about what you're doing. Okay, so flooded lead-acid batteries and any other kind of battery that requires watering maintenance. So nickel cadmium would apply to this as well. I call them flooded lead-acid type batteries. So any batteries that you need to water as part of your maintenance process, they're going to emit a corrosive gas. And so there's a common requirement for battery rooms where you have to put your batteries inside a vented room. And so your room is vented. Often you're putting batteries in an air-conditioned room that has an air vent in it. And so is that air-conditioned room a vented room? Yes, it is. It has a forced air handling unit in it. So then the question is, well, do you have to vent your battery bank? Well, technically, no. Your room is vented. It's in a vented room. Your battery bank is vented. You're not going to get explosive gas accumulating and exploding because your room is vented. But should you collect your gas? And the thing is, flooded lead-acid batteries and any other kind of battery that requires watering maintenance will emit a corrosive gas that has a deteriorating effect on metal. So inside your battery room, you may have an electrician who is used to working in metal flex conduit. They have a lot of battery cables that are thick and only about 5 feet long going between your equipment to your battery bank, and they just put it in some metal flex conduit because it's easier than doing an EMT conduit run. Well, any kind of conduit, EMT conduit, metal flex conduit, if it's exposed to a corrosive gas, it can corrode. And so in a battery room, you have to take a step back and say, what are my location? How do I determine what wire, what jackets, what do I need to specify in terms of my material? Well, take a step back and go back to your locations. Do you have, is there corrosion going on in this environment? Is there water going on in this environment? Is this environment subject to temperature excess? And then you start using that to drive your material selection. So we get some definitions of some different kinds of locations. Let's see, the solar industry has a specific cable, and that solar cable, it's called PV wire. So it's pretty easy to identify. PV wire, it's a single conductor cable, and it's called PV wire. And you ask yourself, well, what did a single conductor cable not exist in the industry before PV wire? And the answer is yes, but PV wire, the only thing that's different about PV wire versus a single conductor cable that's used outdoors by the utility on high voltage systems, like a feeder cable that comes into your building, that can be high voltage, that can be exposed to the sun, that can be in a hot temperature, that can be in a wet location. So why can't you use PV, why can't you use utility feeder service entrance conductors instead of PV wire? What's the difference between those two cable types? Well, you might find that your both cables are listed for a wet environment. And what can be confusing is that these cables can be cross-listed. So they can be listed for a wet environment and a dry environment. And so you might be doing, the difference with PV wire is that it has a thicker jacket. And up on a rooftop, that thicker jacket has some advantages. Now, the thicker jacket is there because solar arrays at the utility scale can go into voltages that are much higher than what you see in a building. And I always like to point out, solar is done at 600 volts, and even your larger, like Best Buy, your big box stores, their building voltage is at 480 volts, three-phase. Solar at 600 volts is very high voltage. It's much higher than your electrical outlet that's at 120 volts. So, this solar as a do-it-yourself project, I don't know. It's a higher voltage than what a commercial electrician is normally exposed to. But anyway, the solar cable has a thicker jacket because it's a higher voltage cable. In utility scale projects, you get all the way up to 2,000 volts. And so it has a thicker jacket to contain that voltage. But a thicker jacket up on a rooftop has some other advantages. If a squirrel chews on your wire, a little bit of thicker jacket might save you. If you're pulling cable under the array and you're not doing good cable management, and you've caught the edge of a metal conduit or fitting or racking with your solar cable, and then over time the racking is expanding and contrasting with temperature, and that rack is tugging on your cable or rubbing into the cable, a little bit of a thicker jacket might be what saves you from ground faulting. And so the solar industry really likes PV cable because it's a very rugged, durable cable for direct burial. As a direct burial cable, if you're taking your cable and just chunking it into the ground without conduit, and you might say, well, can I actually do that? Can I just direct bury a cable? Well, they call it direct burial cabling. And there are some advantages of direct burial cabling as opposed to putting in a wire and conduit. Such as temperature. You might have a cooler cable in a direct burial run rather than if you entrap it in a conduit. And also conduit, it does provide physical protection. I'm not saying to not use conduit, but it doesn't have all the advantages that you think it has in terms of being able to just put in wire and re-pull wire and put in wire and re-pull wire. Conduit can break, and then it becomes a wet environment. And so the point is, you might be on the job site, going back to this solar industry specific cable, and we're talking about wet locations and dry locations, because you might think, well, a wet location, that is more rugged than a dry location. Dry locations are wimpy. They're for inside your house, and you don't need to worry about dry locations. So with dry locations, you're using cheaper traditional building wires that have really thin jackets. You don't need to worry about moisture. And so you are buying solar cable for up on the rooftop, and maybe you buy a big spool, and you get to the point where you're ready to go into the building with your cable run, and you say, well, can I just take my solar cable that is rated for the hottest part of the rooftop for a wet location? You would think that you could just put it into conduit and run it into conduit down to your electric service panel. You know, that's a dry location. If it's good for a wet location, certainly it's good for a dry location, right? Well, it all comes back to maybe, maybe not. You know, it has to be cross-listed for that dry location. And you might say, well, that's ridiculous. You know, why does it need listing? That UL listing is expensive. It's just driving up my project costs. Well, it might be that that thicker jacket causes the wire, when it's contained inside a conduit rather than out in the free air, it might cause that wire to heat up. And so it might have a different, you know, reaction to being enclosed in a conduit than a thinner jacketed wire. You know, PV cable in general, when it's cross-listed to go inside of conduit, and it usually is, you know, you get caught up because it has that thicker jacket. And if you're just using generic rule of thumb guesses on how many number 10 cables can fit into a conduit, you might surprise yourself if you're using PV cable. You know, the same number of utility service entrance conductors with thinner jackets cannot, you take an equivalent gauge solar cable and you wouldn't be able to fit that same number of conductors into the same sized conduit. So, you know, you don't want to neglect your locations. You know, locations may seem a little bit obvious to you, and but the problem is the equipment you deal with in the solar industry can give you a false sense of security. You know, you don't want to neglect your environment. That might be a bit on the nose for a solar design program, but just because your solar equipment is robust and designed to withstand the elements, that does not mean that uninstalled components have the same weather ratings as installed components. So obviously, solar panels are designed to go outdoors and withstand the elements. And you can find inverters that are intended to be mounted on the rooftop. And so whether it's microinverters or DC optimizers, you know, if it's a roof mounted product, it has all the most robust environmental ratings and listings, and it's been tested and designed for that purpose. And so you get to the project and you say, okay, I have all these weatherproof inverters and these modules that are weatherproof. Well, that's assuming that the system is all installed and wired up together. And you might actually get onto the job site and maybe the wires that are up onto this junction box are not installed yet. So here's our junction box. And you might have an electrician coming all the way up and landing on this junction box. You know, that would be, you know, your conduit going into from a dry location into a wet location. Those wires may not be there, and your solar installer may not want to energize and wire up the array on the module to box connection, because he knows there's an electrician with no solar experience doing this part, and he doesn't want to energize this box with his DC system until the electrician is out of there. And so that's where it ends. You leave the modules up on the rooftop until the electrician comes on the other side of the project scope, ready to complete their job. But in the meantime, your connectors coming off the back of the solar modules may remain unplugged. And something that is not fully installed does not have the same weather rating as something that is installed. These inverters are designed to hang on a wall. You know, they could be a NEMA 3R inverter, but if it's sitting on its back on a pallet, it will not have the same weather rating as being fully installed, where maybe these conduit entry points that come from the bottom are not watertight. And so they only get that NEMA 3R resistance when the inverter is hung on the wall. And so you could be a solar installer where you're putting all these electronics on a racking system, but maybe the modules have not arrived yet. And so you're putting your microinverters on the rail and then letting them sit for a while until the solar guy does their job. You might be the solar guy waiting for the electrician to come onto their job, so your modules just have these wires that are hanging out the back of them unprotected. And even things like dew and ice in the morning on a colder project site, or just the modules sitting in a humid environment with a tarp over them, to protect from rain, but it also gets condensation on the inside of the tarp dripping down onto the box that the inverter is in, and that can get into the inverter. And even though it might be a NEMA 3R inverter, it's not as watertight as you think it is because it's not fully installed yet. And so, the point is it might seem obvious, a wet location, a dry location, a hot location, inside of conduit, outside of conduit, corrosive or non-corrosive, but it's failing to think about these locations is where you can really mess up your material storage and cause expensive project mistakes. So let's look at some a little more technical things about these environments. We talked about temperature sizing, and so now what we see in this picture is that let's see, we're in the attic here, and then we're going up into a roof-mounted junction box. And so you might ask yourself, well, this is a wet environment, this is a dry environment. Inside the conduit itself, where does the environment magically change from a wet environment to a dry environment? Is it a dry environment inside the first box that you land on? Is it a dry environment inside this conduit? And so you might be using wet rated conductors, and you might have a wet rated box, and then in here you might have a dry rated conductor. So do you have to bring the dry conductors up into this box where it's a wet environment, or do you have to continue to use your wet rated conductors all the way onto the first box where you land on? Where is the line between a wet environment and a dry environment? Well, this is actually why there's a requirement in code that says you have to seal the inside of your conduit whenever it crosses any temperature differential, actually. So not just between the roof and the attic, but if you're going from a unheated space or an unconditioned space to a conditioned space, just having a temperature differential can cause condensation to accumulate inside the conduit. And so thus just the humidity in your air can cause it to rain inside your conduit. And where do you think this water goes? Well, it drips down into here. And so now you have water inside of what should be a dry conduit. And this water can accumulate and go all the way down the wall into your inverter and start dripping into your disconnects, your fuses, your inverters. It could be, I've seen it on a porch where you have underground cables coming up from the earth and landing on an inverter on the porch, and you open up the inverter and there's water sitting in the bottom of it because the inverter is watertight. And so it's trying to keep water out, but it's also keeping water in. And so you might, at that point have to drill a weep hole into your inverter. You might find yourself asking, well, I'm supposed to have a weatherproof inverter, and is the only solution for me to drill a hole into my casing to let the water out? And yeah, you may need to think about, putting in a box upline for wire terminations. Maybe that external disconnect switch is actually not such a bad thing, because you can have water weep out of that disconnect switch rather than going into the inverter. But technically, you're supposed to seal this between the hot environment and the cold environment to avoid that airflow, avoid that condensation accumulating inside the conduit to begin with. So this conduit, if it can be rated for a dry environment all the way up to that penetration point, but that's assuming that you're sealing the conduit. And so you might find yourself doing an install. We recently did one where it was a standing seam metal roof, and there's a roof cap that goes across the roof and a little 1-inch gap in that roof cap. And so what we did, this was a metal roof, so we didn't want to drill through our metal rooftop. We also didn't want the conduit to run across the roof. And so we said, well, can we go into the roof cap and run our conduits down through the roof cap? The answer is yes. And so the question is, well, how do we do that? And we put a fitting in the roof cap that we could land the conduit on this point of entry onto a fitting. And so your fitting may have one big hole in it. Let me pull up my pen so I can illustrate this a bit better. So you might have, what we had is a Z purlin. And so here is the roof cap, and here is the bottom of this kind of standing seam rooftop. And the roof went over it, and there's this little shield that gets installed, and we put a hole in that shield to route our conduit into the hole. You might say, well, is that code compliant? Can we just drill through the roof cap and go into our building? And as far as National Electric Code goes, yeah, it is compliant, but what you have to comply with is going from this hot, wet environment into this conditioned, colder environment. And so you put your fitting in, and that fitting has a hole, and you take solar cables and you cram them into this hole. And so you have one solar cable coming in, and another solar cable coming in, and another solar cable coming in. And I say, well, there's still gaps of air in that hole. And if you leave that gap there, the moisture from the outside can get into the inside and cause it to rain inside your conduit and cause a leak down the line. And if that water stays inside the box and you're in a freezing area, over time, the winter hits, and now you have ice inside your box, and that ice starts trying to break your box apart. It can eventually, small problems can result in big problems. So instead, and let's see, let me get back onto my presentation. Instead, you can find fittings that and what always screws me up is I got my presenter tools in PowerPoint and my presenter tools in GoToMeeting, and so sometimes I have to figure out which one I'm on. But back on this hole, you can find a fitting that is just a 3/4 inch hole for putting a 3/4 inch conduit into, or cable into it. Or you might be able to squeeze 4 solar cables into it. But there's actually a fitting you can find that comes with a seal and 4 little holes in it that are sized for each number 10 conductor to go into. And it costs a little bit more money, and sometimes you can't find it off the shelf at Home Depot, but you have to order it online. And so the question is, well, am I going to do everything by just going to Home Depot and buying these general equipment? Maybe a junction box, but not a solar box, or a EMT conduit compression fitting, even though I'm trying to put 4 solar conductors into one hole. and you usually find that there's more than one reason in these specialized components, where not only are we spacing the conductors out so that they don't overheat, but also we're sealing the hole so that moisture doesn't get in and out. So if there's a specialty kind of balance of system material item that looks like it does a unique job, then it's worth looking into. All right, let me try and erase some of this stuff. There we go. All right, so 110.14c, electrical connections with temperature limitations. The temperature rating associated with the ampacity of a conductor shall not exceed the temperature rating of any other connector, termination, or conductor of any other device on the circuit. So often you will find that you need a junction box or you need a disconnect switch. And maybe if you had ordered it from your solar distributor, they would have given you a solar disconnect that had been listed for a higher temperature rating because it's a solar device. But then most of your utility disconnect switches, they're outdoor rated. They have the right voltage, the right service, and they're rated for outdoor use. You see them all the time on the outside of a building, but it's not ever intended to be placed on a rooftop, and so it's not rated at that higher temperature rating. It's rated at a lower temperature rating, and that might be all right. You may never get up to that higher temperature rating on your rooftop anyway, so it may be perfectly appropriate for you to use that disconnect switch on top of that rooftop. And what we learned in other classes is that if you don't know what your rooftop temperatures are, you can always go to PV watts, and inside that hourly temperature data in PV watts, it'll tell you what your ambient rooftop temperatures are. The issue is if you have a disconnect switch where you have an electrical connection coming onto that disconnect switch, and that disconnect switch only has a 75C rating, and you've been using solar cable and solar equipment that's rated for 90C, you may find that you have to redo your temperature calculations for a 75C rating. And in particular, when you have to do a 75C calculation for that terminal in that box, simply because it doesn't have a 90C listing. And so you need to go through all of your equipment and say that if it might be that 75C is sufficient, and it usually is sufficient, but what it says is the temperature ratings associated with the ampacity of the conductor shall not exceed the lowest temperature rating of any connector, termination, conductor, or device. So often, even if you're using 90C equipment, you'll do your calculations at 75C. Often with solar cable, you're upsizing the solar cable anyway. So this is you do your calculations at 75C, and you're not going to make a mistake. Only when you get into kind of fine tuning your design do you really need to be a little more aggressive than that. And you might say, well, where do I get all this information on what temperature rating or voltage rating or cable type it is? If you go to your hardware store, they're going to have a wall on an elevator with spools and spools and spools and spools of different wires. And you look at any cable, and printed on its side is the temperature rating, the cable type. This is TC cable, 90C, 600 volts. You get the gauge of the cable, the listing of the cable, and even things like if it's rated for direct burial or environmentally rated for sunlight exposure, that comes up on the sides of your cable jackets. Eventually, when we talk about, we're going to get to Article 310, and that's where we're talking about performing these temperature calculations. And what you see is if you have equipment that's listed for higher temperatures, depending on what your temperature is. So if you're in a 120-degree environment and your cable, that's your cable that's like might be a 90. Well, I don't know. If you're using 60C cable versus 90C cable, you have to derate your 60C cable because it's being used in it's rated for 140 degrees. So can you use 60C cable can you use 140-degree cable in a 130-degree environment? And remember, electricity produces heat as well. So if your ambient temperature is 130 and your electricity is producing heat, putting it in a 140-degree environment may not be the best idea in the world, but is it a danger? And code is concerned about determining if it's a danger or not within reason. They're not taking on the liability of your own personal design practice. Well, no, you can use this cable that's rated for a 140-degree environment in a 130-degree environment, and they give you a kind of a fudge factor to say just derate the amperage rating of the wire by 40% so that the heat from the electricity does not become a problem. Well, guess what? If you use a cable that's rated for a 90C environment instead of a 60C environment, it's not up at the top of its temperature rating yet, and so that 40% derating is only 25. That 60% derating is only a 25% derating for your higher temperature wire, because it's listed and it may have a better jacket for those higher temperatures. So, as we mentioned, where do you find temperature data about your job site? Well, a handy dandy PV Watts calculator, that the same calculator you can use in a matter of minutes to do a energy performance estimate. It's all free. It's put out by the Department of Energy. We have all these public weather monitoring stations at airports, at military bases that are collecting weather data all the way back into the 60s. And so what PV Watts does, it's a governmental software, and it gives you access to this weather data and puts a solar performance calculator on top of it. Where a lot of people fall short is they get to this screen where it tells you the annual production and the month by month production. You can actually download this data on an hourly basis. And when you get into that hourly export, it gives you all sorts of really great stuff that's useful in off-grid design in particular. Like you can look at your array radiance as a function of time of day. It's also as a function of weather. So in off-grid design, from the PV Watts data, you can see how many overcast days in a row are typical to your area. Well, you can also get your module surface temperature. And the surface temperature, we talk about standard test condition, what the module is listed at, and that module is listed at a 25 degrees Celsius standard test condition. And what we can see is on this is probably for December or for January. And what we see is that on January 1st, there's a year column here. It's probably for January at high noon. Our solar module is getting up to its listed temperature. And so you might say, well, what is my solar module getting up to in the summertime? That information is on PV Watts, and you can use that to do your performance derate calculations. You can find out your maximum system power. Now, another thing you can find out is what we were just talking about. What is your rooftop surface temperature? And you can find that on PV Watts, where you'll see when you choose the difference between a ground mount array and a roof mount array, you'll see that ambient temperature climb. And so we want to ask ourselves, well, how hot is a rooftop actually? And not in Celsius, because we're American and we use Fahrenheit. And so how hot does it get? Well, let's go and look at the extreme. We're in Phoenix, Arizona. And let's say we're on a 98-degree day outside in Phoenix, Arizona. Your solar module can get all the way up to 61 C or 160 degrees Fahrenheit. So actually, we go back into our tables in section 300 that we haven't gotten to yet, but we get to our ampacity tables, and we see this: 60 C wire, 75 C wire, 90 C wire. And we see that up on the rooftop, it can get above 60 C and approach 71 C. And so now we have a perhaps healthier respect for 90 C wire up on a rooftop. You know, we see that we can't really use 60 C and we can't really use 75 C. We kind of have to use 90 C. And then you look at all these tables, table upon table upon table in National Electric Code. And then, well, where's all this data coming from? Well, we see that if you're using a 60 C wire and you get into elevated temperatures, eventually the D-rate trend, this table will end, and these will keep going until they approach close to 40%. But eventually your 60 C wire cancels out, you know, pretty shortly after it exceeds its temperature rating. You know, Article 110.26, spaces about electrical equipment. So this is a good article to spend some time on, because the layout of your equipment room, especially when you get into battery systems, you know, you might have your solar inverter plus an extra battery inverter. Maybe you have a solar inverter, a battery inverter, and the input from your generator, or at least a signal wire out to your generator. Often in a battery room, if you're using flooded lead acid type batteries, you're going to want water in that room because you're going to be watering the batteries. There's at least a faucet. You know, electrical equipment has to have its own dedicated space. And so you might say, well, is this air conditioning duct a violation or not? Well, there's a 6-foot limit on that space. So as long as this duct, you know, they're really cutting the line right there. You know, that's probably exactly 6 feet. If it was less than 6 feet, it would have been a violation. But there's also workmanship issues here that your inspector could pick you up on. And also, we look at this water heater, and we can see that originally the electrical system and the water tank, they had a lot of space in between, but then computer technology has crept in, and now we have some electrical wiring that is starting to encroach on this plumbing space. You know, the spaces about your electrical equipment have to be dedicated. And then we get into the depth requirements. So there's actually different depth requirements on if you have electrical equipment on both sides of the wall, or if it's freestanding in the room. You know, in general, your working spaces, you need to have about 3.5 feet of space in front of the piece of electrical equipment. You know, I like to think about this just in terms of practicality. That's one person being able to stand in front of the equipment and kind of extend their arm out and comfortably work in the area. As far as the width goes, 30 inches or the width of the equipment space. So if you have a tiny little box, you know, it needs to have this kind of movable 30-inch zone around it. or it can be up to the width of the equipment. So the idea is that a person who's about 2 feet wide can be standing in front of that box and comfortably working with it. Now that person might be shifted to the right or to the left, but they still have space to stand in front of the equipment and work at it. And then we get to the height of the working space, and it's 6.5 feet tall, or the height of the equipment, whichever is greater. And so you might have a giant piece of equipment that's 8 feet tall, and that's the cutoff. If it's 6 feet, if it's a 4-piece tall equipment, your air conditioning duct needs to be at least 6.5 feet above it. So in a very real way, here we have the this storage room. This was what the architect came out with for our room. That's a dedicated room in the garage of a house that's going to be that is an off-grid house. And so I said, okay, we're going to have a freezer here and some plumbing here and our battery bank here and the generators on the outside of the building. So we're going to put the battery bank near the generator, and then we have some cabinet and shelves and a door. And so you might think, well, how much space do I need for an inverter room? How much space do I need for a solar room or a battery bank? Let's just take a look. It depends on your battery technology. Lead acid takes up a little bit more space than lithium ion. It depends if you're doing off-grid. It requires a much larger battery than on-grid. But here are off-grid lead acid batteries. And these are the ones we ended up with, and we had 8 of them. And they're over 3 feet long, 2 feet high, and 10 inches wide. And so these are gel batteries that are on the side, but just imagine coming out of the wall. Here's our wall, and we have a battery that sticks out, over 3.5 feet. It's 2 feet off the ground. They're heavy as all can be. They weigh 1,000 pounds each, and there are 8 of them. So you have to think about your concrete. 3,000 pound concrete. You might have to actually take a look at that and maybe distribute the weight over a larger surface area. Batteries are heavy. And so we have 8 of these batteries. So our batteries alone are going to be 8 feet long. Here our room is 20 feet. And so we have room here for our battery bank, but they're going to stick out 3.5 feet. And so they're going to be right up to that point. So our batteries, they do have some room there. This is our inverter system. And we have 4 charge controllers that are about 1 foot wide each. A little bit less than that. They're kind of like the batteries, about 10 inches. Then we have our electric service panel that everything is kind of wired into. And there's a DC side and an AC side, and the generator comes into that as well. And there's a little bit of wiring that occurs here too, but this is like your line side master service panel. And I recommend not doing load side connections where you go into your existing panel. Let me draw this a little bit better. But here's your power lines coming in from your utility, and you got a little utility transformer. The power lines go into your building. And then on the outside of your building, you have your electric meter. So you have the power lines coming in to the electric meter, and then you go into your building. It's a terrible layout. Erase this. And so what we have is your meter, and then your electric service panel. And for residential systems in particular, it's common to take the solar array and locate it at the bottom of the bus bar. And essentially, you're feeding the panel from 2 sides, from the top and from the bottom. And you can only do that by about an additional 20%. And when you do a supply side connection where you put in a dedicated panel that's just for on-site energy management. And so this is your dedicated panel for your energy systems. And that might have a transfer switch into it. You know, this panel can be landed between your utility connection and the whole house. And so a solar array may only be able to power a critical load panel that's kind of off the main, whereas a line side connection can supply the whole house. And instead of just using an additional 20% at the bottom of the bus bar, a supply side connection, you know, it doesn't matter if it comes from the utility or from the solar array, it can supply 100%. And so, you know, a solar array may be an array that's sized to be 20% the size of your electric feeder is enough to offset 100% of your electric bill. You know, a solar array is on for about a third of the day at full power. You know, your house is only on about a third of the day and nowhere close to full power, you know. So it's very common for a solar array that by the breakers, you know, you have a 200 amp service and it's a 40 amp solar array. It's very common for that 40 amp solar array to net out the bill. But if we ever wanted to expand that array, you know, if you want to do electric cars and then your electric usage goes up, or if you're at the top of your capacity and you want to add a battery and you want to put the battery on its own inverter, you know, all of these things are going to start increasing the amperage of your system. So a lot of systems, they just have one solar array on them. But then you might want to add a battery system right next to it, and that might mean that you have twice the amperage. You have 80 amps instead of 40. All of a sudden, that load side connection is too small. You know, with a line side connection, if you have a dedicated service panel for your batteries, for your solar array, for all of your on-site management systems, in our community solar class, we talk about, you know, you might not just want to decrease your energy use with solar, there might be a reason to increase your energy use for energy management. You know, flooded lead acid batteries, they like to have a constant steady draw off of them, and there's more than one way to skin a cat. You know, Bitcoin mining. Bitcoin is a digital currency, and to mine Bitcoin, which you literally is a computer and you plug it into the wall and connect it to the internet, and it burns electricity and it gives you money. So Bitcoin is, if you're mining Bitcoin, you're converting electricity into money, and it only makes sense if you have access to dirt cheap electricity. When you have access to dirt cheap electricity under demand rate structures, where you're paying for demand and not so much for consumption. And in the future, when we go into cell phone style electric bills, where you might have a fixed meter fee from the utility and then the energy is cheaper, or you're buying a block of electricity that's a function of energy and power, and your question is, well, how do I fill up the entire block so I have the most efficient electric bill possible? You know, there may be reasons to be increasing your energy use as well as decreasing your energy use, and we can't really predict the future. So having a dedicated service panel that has a transfer switch where you can plug in multiple inverters and stuff all together is a good idea. And so if we assume that our solar inverter is going to be about 30 inches wide, and our battery inverter is going to be about 30 inches wide, and our service panel is going to be about 30 inches wide, and then we have our battery bank that's about 8 feet wide, and then when you get into batteries, another issue is that you want your battery bank to be right next to your inverters, because this cable between your battery and that service panel has to be very short. The solar array can be located further away. The battery inverter itself, I guess it could be, it kind of needs to be close. And so maybe going back to our array room layout, this is what's come back from the architect. But we say, all right, well, one problem is, I have a 8-foot long battery bank. So here's 8 feet, but it needs to be accessible. And so depending on my watering system and my equalization, you're supposed to be testing every battery cell as part of your maintenance. Maybe it's a maintenance-free battery. And if it's a maintenance-free battery, it can be shoved up against the side of that wall. If it's a maintenance battery and you have to get all the way into this corner to test the cell, you'll actually have to put, some clearance on that, and that might have to be 3.5 feet when you stand facing that cell. And so now this battery bank that's 8 foot long is going to have to stick out at least 11 feet into the room. And then you have a problem with working space where the depth of the equipment. So let's, we got the width of the working space. It has to be 30 inches. And so if you're trying to maintain that back cell, you have to have 30 inches of space. Well, the batteries stick out 38 inches. So you got 30 inches. The depth has to be 3.5 feet. So now our battery wall at a minimum has to be 3.5 feet on either side of the battery. And our batteries is 8 feet wide. So now our room has to be at least 15 feet. We got 20 feet here, so we're still all right. But then we see that the batteries and the inverters need to be kind of next to each other. And the problem with these panels is that they're only 9 inches deep. And remember, our batteries stick out 38 inches. And not only is there a width, a height, and the working space depth requirement, there's an additional requirement that says, sorry, I got my phone connected to my email, and I opened my email to log into the meeting. So let me just turn that off real quick. There we go. Okay. So there's also a requirement that says within a dedicated electrical space working area where nothing except electrical equipment can be. So not plumbing, but our plumbing's over here. We have a freezer here. Maybe we want to move that over there. But above or below the electrical equipment, you can't have anything extending by more than 6 inches. And so if we wanted to have our battery bank and it's sticking out 3.5 feet from the wall, and then we say, okay, well, we want to put our inverters and stuff right next to it. Okay, well, we got 9 inches here and it sticks out 39 inches. So we can have kind of our 30-degree working space. Let's not worry so much about that. Now we have a 30-inch inverter, a 30-inch solar inverter, a 30-inch battery inverter, a 30-inch service panel, and then for our system, we also have these charge controllers coming in from the solar array itself, and these could be located somewhere else. They don't have to be located right there. And so what we're looking at as a minimum size to our inverter wall is about 3, 6, 9 plus 3.5 plus 3.5, 7 plus 8. Now we're looking at a 25-foot inverter wall to be code compliant. And so, just by winging it and saying we're going to put everything along this back wall here, and you might think you have plenty of space because you have a 20-foot long wall that's completely empty. And who shows up on a job site and there's just 20 feet of vacant space in your utility room for you to use? That's very rare. But it turns out, no, what we're going to have to do is, to be code compliant, is catty corner the system across these two walls and eliminate this door frame here. So the off-grid battery systems can get quite large, or it might be that you have your Tesla Powerwall plus your solar inverter plus this integrated service panel, and that at a bare minimum for an on-site kind of power wall for your on-site system, what you're looking at is at least 9 feet of dedicated working space. And that's assuming you're dealing with maintenance-free batteries. So, at least 9 feet of space on your wall, just make it an even 10 is a good layout for your future residential electrical room based on code. So let's take a look at some of these pictures. Are these rooms code compliant? Well, if you actually have to take a hydrometer and stick in a stick and measure the specific gravity of that nickel cadmium battery, that working space is not accessible. You need 3.5 feet of working space there. And if you have another piece of equipment here and another piece of equipment here, and your back is to electrical equipment, that's where code might go a step further and say, well, generally that depth requirement is 3.5 feet, but there could be a condition where it's more than that. Guess where that condition is more than that. That's when you're kind of back to back against electrical rooms. So, what you can see here in this room, this is a violation. The violation is because, we have the kind of the same issue here, but also this panel sticks out about 9 inches and these batteries stick out about 38 inches. And so there's more than a 6-inch difference between these two panels. You don't want someone leaning over the batteries to access the service panel. So, and what's nice about lead acid batteries is in the future, they'll be swapped out with lithium ion, and that will no longer be an issue when the battery bank is smaller. So here we have two batteries, and these were both pulled off of the battery manufacturer's website as being one of their highlighted projects, and they have code violations in them, and it's all array room layout stuff. Okay, so let's talk about the definition of ampacity, voltage, and nominal voltage. So for ampacity, we have the maximum current that a conductor can carry continuously under conditions without exceeding its temperature rating. And so, your cable is rated so that it can carry all of that current and not burn up and smolder. If you ever see in the field, if you ever see a cable where the jacket of the cable is smoldering, there's a temperature calculation issue. Either you didn't do the 75C calculation for that disconnect, and that terminal on the disconnect is heating up, and that's causing your cable to smolder, or you messed up the temperature calculation in the cable itself at 90C. Maybe you undersized your cable, didn't allow for derating inside of conduit or something like that. Voltage, the difference of potential between two conductors of the circuit. And I think it's very difficult to understand what voltage is, and everyone refers to voltage as potential. I think even though it's voltage potential, it's not energy potential, it's voltage potential. What I think about voltage is like a mountain. And so you can have a boulder at the top of the mountain, a boulder at the bottom of the mountain, middle, halfway down, and then the boulder, down at the bottom. And that boulder down at the bottom is not dangerous. It's at 0 volts. There's nothing. It's just going to sit there. If someone goes and pushes on that boulder and you're standing there, if it's a pebble, it's not going to do anything. If it's a giant earth ball, it could crush you. So higher voltage is more dangerous than lower voltage. But in terms of this, I think about high voltage being at the top of the mountain, where someone pushes that off the cliff, it's going to do a whole bunch of damage as it rolls down. Then you have medium voltage and low voltage. Fiber optic networks, computer networks, they're all at 2 volts, 6 volts. And, you get a specialty contractor license if you're a fiber optic contractor because you're dealing with lower voltage systems. There's this argument that says solar contractors should be a specialty license because regular electricians don't know solar. Really the argument on why solar should be a specialty license is because it's a high voltage system. They should be subject to more rigorous regulations than a standard electrician if there is going to be any kind of specialty license. Usually it's the other way around, that your solar contractor knows less about general electricianing than the electrician. They just know more about the solar technology. So then we get voltage to ground, which is you take your voltage circuits and test them to ground, and you measure the potential between the two. Then it says for ungrounded circuits, the greatest voltage in a given conductor and any other conductor of that circuit. So it might be that you have a neutral wire and there's power in it, and between your 120 volt circuit leg and your neutral wire, you might be measuring 60 volts. You would still consider that to be a 120 volt difference, because the greatest voltage difference might be when there's no voltage on the neutral and 120 volts in your leg. And then we get to nominal voltage. And nominal voltage is kind of the nickname for voltage. Voltage, we talk about 480 volts or 120 volts, and we see how you have a 120 volt circuit, but maybe your appliance is listed at 115 volts, and well, why is that? And well, that's because there's inefficiency in your cable, and by the time the 120 volt circuit makes it to your 115 volt appliance, it's lost some power. So that manufacturer thought that it would be smarter for them to say, no, it'll work at 115 volts, because they know that there's going to be voltage drop, and they want to assure you that their system will turn on if you plug it into a 120 volt circuit, and they're just overthinking things. A solar inverter, you say, oh, well, it synchronizes up to the grid. Well, what does that actually mean? That solar inverter is operating at a higher potential, at a higher voltage potential than the grid. The solar inverter is trying to be at the top of the mountain. Your grid might be halfway down the mountain, so that it can push its electricity out onto the grid. You push electricity from a higher voltage down to a lower voltage. And so we might say, okay, the grid is at 240 volts, or our electric service is at 240 volts. So our nominal voltage from our solar inverter is a 240 volt AC inverter. But it might be actually operating at 245 volts to push that electricity out onto the grid. And so there's a concern about, if you have a dumb inverter, let's be stereotypical and say you have a dumb sports jock, and you just tell him to run in a straight line all the way to the end of the field, and then he runs into the fence and he trips over the fence because he's dumb. He's doing exactly what you told him to do. The concern is that a solar inverter might be the same way, and that the solar inverter is dumb, and there might be a situation where the grid power and the solar power are fighting with each other, and so we have to put safety provisions into this. And we also have to be more careful when we're combining just dumb solar inverters that are not intended to be energy management devices, but are just designed to dump all of their power onto the grid, or all of their power into a battery bank, that the system is well sized so that we're not exploding our batteries or backfeeding the grid when we're not supposed to, or backfeeding a generator. And there's a number of ways we can do that. And often these ways have to do with mechanical switching so that there's a hard disconnect. Talk about that a little later. Well, then we get into regular electrical stuff. We have branch circuits. Branch circuits are our lighting circuits and our ceiling fans and stuff like that. And you know, we talk about how in the DC realm, we call our DC circuits strings, and that's really just to differentiate a AC branch circuit from a DC, you know, branch circuit. You know, the industry jargon is to say strings for DC circuits and leave AC circuits being branch circuits. But you really could have DC branch circuits too if you're being technical and not using the industry jargon. We have continuous loads, and this is where, you know, you have continuous loads and you have non-continuous loads. So what's the difference between a continuous load and a non-continuous load? Well, maybe, you know, this outlet is not being used 24/7. Maybe it's only being used whenever you have dinner in your dining room. It might be a chandelier or something. Or it might be on 24/7. It might be a security system. So you have a continuous load or a non-continuous load. Continuous loads are currents that are expected to run for more than 3 hours. So is a refrigerator a continuous load? You know, don't get hung up on that duty cycle where the refrigerator clicks on and clicks off and clicks on and clicks off. It's plugged into the wall. It's operating 24/7. It's a continuous load. Is a solar array a continuous load? Now, a solar array, it's only on when the sun's up. It's not on at night, but it's a continuous load because the solar array under normal operating conditions is on for more than 3 hours. And so what's the difference between a continuous load and a non-continuous load? Well, continuous loads are on more often than non-continuous loads. So which are more dangerous? You know, continuous loads or non-continuous loads? Well, from the eyes of code, a continuous load is always drawing that amperage, and that's going to heat up a little bit more than non-continuous loads. So often you're going to have on a continuous load an additional 25% safety factor, whereas with non-continuous loads you don't. So a lot of equations in code moving forward are going to be like 125% of continuous plus 100% of non-continuous, and they're giving an additional little bit of a safety bump to continuous loads. And so when you're doing your circuit sizing, you're thinking about, well, what amperage am I calculating a solar array at? You know, you might have its nominal output, but then you might have to give it an additional 25% bump because it's a continuous load. Branch circuit conductors shall have an ampacity of not less than the non-continuous load plus 125% of the continuous load before any adjustments or corrections. So we see early on in code, it's saying if you have a load or a constant amount of power flowing through a conductor, you have a 25% correction, and then you add on non-continuous loads on top of that. So by now, which of these loads are continuous? You have a dishwasher, you have a refrigerator, and an air conditioning unit. It might, the refrigerator and the air conditioning unit are plugged in 24/7. The dishwasher is not being used on a constant basis. So it's the dishwasher is the non-continuous load. The fridge, the air conditioner, the solar array are continuous loads. Then again, the dishwasher may be considered a specialty equipment or even a general equipment that's regularly used. So we have to check other parts of National Electric Code to see if other more specific rules apply to dishwashers. And so Articles 200 is kind of establishing the theory of electrical safety. And it'll get more specific as we go along. It says branch circuits, different rules for over 600 volts and under 600 volts. Well, we're really dealing with 600 volt circuits here. Motor circuits are defined later. And generally with motor circuits, instead of having a 25% corrective factor, it might be more like a 15% corrective factor. And often that's because these motors are more controlled than just a dumb continuous load. And so that extra level of control, maybe there's additional fuse requirements, additional overcurrent safety provisions that are applicable to a generator. So it might not be that the generator's simpler, it might not be that it's cheaper, it's that, because it's more complicated with more protections built into it, they don't have just this brute, dumb 25% overcurrent applied to it. But that's specialized, and we'll get there. Okay, so then we have not to exceed 3% or 5% at the furthest outlet. This is interesting. What that refers to is voltage drop. So in code, the maximum voltage drop to the furthest non-continuous load is 5%, and then 3% to the farthest load or continuous load. And so what that means is in solar, we're really designing to no more than a 3% voltage drop. That's the minimum. But then, often in solar, you're upsizing your wires to mitigate voltage drop beyond that. Now, I see a lot of kind of misrepresentations of DC circuits and DC electrical theory. One common one is that we don't have DC circuits in our home because AC is more efficient than DC. But what does that actually mean? I mean, when you have a cable and you have electrons flowing through that cable, DC is they're flowing from that high potential to that low potential. And so, isn't that boulder rolling down the hill? With AC, the electrons, instead of going from high to low, they wiggle back and forth. And they kind of stop and run the other way. So it's like, imagine you're a sprinter and you want to do a 100-meter dash, or you're elementary school kid doing a PE exercise and you're running back and forth between the 10-yard line 5 times. You run the same distance, you might do the same amount of work, but which seems more efficient to you, the 100-meter dash or running back and forth in the same direction 5 times? That kid is going to be more worn out than that sprinter. Let's ask ourselves again, is AC more efficient than DC? Now, the answer is no. You get more heating from induction, you get more inefficiency in an AC circuit than you do in a DC circuit, theoretically. In the AC, they call them eddy currents. to describe the additional losses associated with AC that you don't have with DC. And we're really splitting hairs because it doesn't matter so much. You know, in electrical design, you're not really deciding so much if you're doing DC or AC, but it's more like, okay, your solar arrays at 500 or 600 volts, your power outlets are at 240 or split phase, you know, all the way down to 120 volts. How do we get to point A to point B? Now that's where we have to convert our electricity, you know, to step down the voltage, to step up the voltage, to not have it be continuous, but instead to have it wiggle back and forth in place. You know, we have to transform the voltage. And it turns out that it's more efficient to manage and transform and step up and step down AC electricity. That the actual little transformers and pieces of electrical equipment for increasing and decreasing voltage are more efficient. And so you know, the transformers are like those brown pieces of the Tinker Toy set that everything plugs into. The transformers are better if they're AC, and so our grid is AC. It's not that the actual electron in that cable is more or less efficient. It's about the same. The only difference is these eddy currents, but that's really splitting hairs. And we're on AC because of the actual transformer equipment being more pragmatic if it's AC. So, do we need to have AC circuits in our home? Well, again, it's probably more pragmatic for you to do AC. AC has a lot more ingrained support, but having dedicated DC circuits is not out of the picture. You know, so if you're in a tiny house or in an RV, you may have a 48-volt lead acid battery bank, and you might say, well, do I need to go through my inverter? You know, every electronic device is not on AC electricity, it's on DC electricity. And that thing that you plug into the wall is an inverter that takes the AC electricity from your wall and puts it into your DC device. So, you know, it might be more efficient for everything to be on DC, but we still have all different kinds of voltages to step up and step down. And so we're still going to need some kind of thing to plug into the wall. And in the solar industry, you know, that might be the choice between, do you want to use a microinverter or a DC optimizer? And it might be easier to use the microinverter. It might be a little bit more cost effective in the long run just to stay DC for manipulating the power. You know, it really just depends on your component cost. But the real reason why we don't have circuits coming off of our 48-volt battery banks is because we're at lower voltages rather than higher voltages. So if we're designing around a 5% voltage drop to the furthest outlet, what that means if you have a 48-volt battery bank is you can only go 80 feet with your wire run. And so that really constrains your ability, your house size. Now, if you have a RV and you're on a 12-volt battery bank, you can barely make it to the end of the RV before your devices just flat out won't work. And so, you know, while a DC circuit might work for a tiny house or a hunting cabin or an RV, you may not you might specify DC circuits in your home, but they might just be around the battery room itself. You know, so you might do a DC water pump, you might do a DC heating element, you might do a DC air conditioner in the battery room itself, and have DC circuits. It's just not standard we're doing the DC circuits get a bad rep because your battery banks are generally at lower voltages, and that just physically constrains how far away you can get. Now then again, is it better if you're doing a ground mount, and you have a ground mount solar array here, and your solar array is often operating at around 400 volts, give or take, and then your house is over here, you know, where is it better to put your inverter? Is it better to put your inverter at the solar array, or is it better to put your inverter at the house? Well, you know, what's best is to put the inverter at the house so that you can take advantages of this high voltage run back to your inverter. What might even be better is to use a DC optimizer system to step up the voltage to 600 volts, basically so that you can push that electricity further across the same cable size. You know, when you increase your voltage, you decrease your amperage. So if you have, usually it's the amperage that fills up the cable before the voltage limits get there. All right, so I don't really know the relevancy of this example in context. I guess what we're going to get into is feeder circuits, but it's time for our break. We've been at this for over an hour and a half, so why don't we take a 15-minute break? It's 20 till now, so let's pick up in 15 minutes. We'll be back at 5 till, so we'll pick back up in 15 minutes. See you at I guess it's kind of a weird time, but we'll pick back up at about 5 minutes till, and we'll talk about feeder circuits. And we're gonna pick back up in just a minute. Actually, we're gonna do a little design exercise quickly when we get back. And I'm happy to use one of your home addresses for the exercise. So if anyone wants to type in their address into the chat box, I'll do a National Electric Code report, show you how to do that real quick for a solar array designed for your rooftop. If anyone wants to type in their residential address, I'll pull it up on the board. Otherwise, we'll just pick previous project of mine and give you a minute to get back to the seat. All right. So let's see. I'm gonna pull up one of my small project scopes. Then we had a client who, essentially he was a do-it-yourselfer, and he had installed this, and what he needed was a permit documentation so that his electrician could drop the permit off based on what had been installed. So he did a little do-it-yourselfer project with the help of an electrician, but then he got to saying, well, did I do everything correctly? And so, you have to go and, it's an iterative process. But eventually it comes time to, while I think it's better to do this beforehand, but you need to get to the point where you can do a one-line diagram that has we saw two solar arrays. He actually had two different solar arrays. So here's a one-line diagram that's code compliant with all the right sizes and breakers and call outs. And we actually had to model this. It wasn't completely automated. We generated these documents in using a software called Solar Design Tool. And I don't want to show you how to use Solar Design Tool, but as we mentioned in our Design Your Solar Roof class, they do provide a month of free access. So if you want to kind of play around with it, essentially what we did is we went in to the system builder. He already knew his array layout. And so in the system builder, we selected the solar module that he was actually using and the inverter that he was actually using. Let's see here. Zoom out a little. So he had two different solar arrays. Here's his solar edge system. And so we can see with the solar edge system, he said, okay, I have one circuit of 14 modules, one circuit of 12 modules, and one circuit of 12 modules. And so we put that in, and then you get into specifying the balance of system components. And this is where knowing about, what we see is, what location are we at? Are we transitioning through the attic where you're going into that dry location, or are we staying up on the rooftop? At what point are we across the roof? What equipment are we using? Are we doing a load side or supply side interconnection? Are we doing a fuse disconnect or a breaker box? And click submit. So you're putting in your array details. Looks like they made it a little bit more user friendly, because it used to be you had to actually specify the wire jacket. So now here we're getting to the point where we actually need to know a little bit of code, and Solar Design Tool does a lot of the code connecting the dots for you. But here we're selecting, what wire are we doing? We haven't gotten into cable jackets yet. When we get into cable jackets, what we'll see is that this little -2 is for outdoor rated cable jackets. And the difference between RHW or THW, that W, this is all wet related environments, and all of these letters actually have meanings. And it might be that one of these is rated for direct burial, the other isn't. One of them is rated for, maybe it's an AC cable and it only goes up to 300 volts. Or it might be higher voltage. Eventually we're going to have to pick out our wire sizes, and we see our temperature ratings already being factored into software. We're going to have to size our equipment ground conductors and stuff like that. But remember, code is a set of rules and regulations. And so once we've picked out how many modules we have in a circuit, and we know a little bit about our environment, the minimums can be automatically calculated, and then we can choose to go up from there. And so what's nice about Solar Design Tool is just by putting in a little bit of data about our environmental conditions, the lengths of our wire runs, it'll generate, not only a single line diagram, and so here's our SolarEdge single line diagram with those 3 different circuits going into our SolarEdge inverter. And then at that point, what I did was I extracted this data. I actually just took screenshots for one project and just stitched the graphics together in Microsoft Paint, actually. Because what we needed to do was just combine this SolarEdge system with the existing microinverter system for an updated one-line diagram. But the reason why I wanted to point this out is if you're brand new to National Electric Code, a great way to, a great next step in learning what you need to know for solar design is to put your array layout into Solar Design Tool, answer a few questions, and then finally you get to electrical calculations and wire schedules, and then you scroll all the way down to electrical calculations, these pages, and you get a National Electric Code report of every calculation that an inspector is going to want to know going into the system. So let's read through this, and then we'll get back into our exploration of code. So we see for calculating the voltage of a solar circuit, that's an NEC 690. We'll be talking about that tomorrow. It's pulling temperature data from other industry manuals, and it's showing you, 690.7 says that you have to adjust the voltage calculation based off a temperature coefficient, and here's how to do that. And so, calculating the maximum voltage of a circuit, it references 697.B and gives you that voltage calculation. Going into wiring and conduit and fuse protection. Here we have a continuous current is equal to the maximum rated output of each optimizer. So in this calculation, we're not adjusting the continuous output of the solar module by an additional 25%. And the reason why we're not doing that is that there's an inline regulator that is controlling the output of the module. And so we don't have to give it an additional 25% because of the use of this particular electronic. You know, it references a chart, an amperage capacity chart that we in section 300 we'll get into. You know, for sizing the equipment ground conductor, you know, here's our reference to table 250.122. And so the reason why I want to point this out is while we're kind of getting through, reading through code, when you actually get out into the field and it comes time to calculate code books or study for the NABCEP exam, you know, here we're checking the base ampacity at the terminal, given the terminal temperature rating has to exceed 125% of the continuous current rating. So that terminal, by the time you get to the terminal, you still have to give it that terminal rating an additional 25%. So you might not know where to go in code, and running a National Electric Code report through a sizing program, you know, Aurora, Helioscope, Solar Design Tool, they all do National Electric Code checks built into the design software. And if you use the design software as a crutch, it can be a good tutoring tool. I'm telling you, you know, what calculations of code are specific to solar design. So I guess what I'm trying to say is just remember that your solar manufacturers have, and your solar design softwares have tools to help you, you know, to guide you along this process. But you might not pick up on all of the nuances of what's going on. So here we have a wiring diagram from Enphase. And often, you know, when I got started in the industry, I didn't know all the rules regarding, you know, what about the conduit that runs between the service panel and the power outlet and the support straps. I didn't know that stuff. So I'd leave that to a electrician who was very familiar with code to figure that stuff out. But we have to enable the electrician to come onto the job site. So you go ask an electrician, have you ever done solar before? They say, I don't know what you're talking about. You hand them a very detailed wiring diagram that might just be a printout from the manufacturer website, and all of a sudden their eyes light up and they say, well, I've never done solar before, but this looks pretty straightforward. I'm just running a double pole branch circuit up to the rooftop, and I have a leg 1, leg 2, neutral, and ground, and really, is it that simple? I'm about to get to work. But you'll miss out on nuances like this microinverter is feeding the bottom of the bus bar, and so it's subject to this 20% rule, whereas if you went into the supply side connection, you could do up to 100%. So let's talk about feeders. Feeders are what supply power to a load, you know, to a service panel. So you have power circuits, line circuits, supply circuits going into a panel, and then you have load circuits coming out of it. Feeders are about supply. So there's a solar circuit, a feeder circuit. Now, yeah, in a sense, there's different rules for higher voltages or lower voltages, but in general, feeder circuits are going to be sized off 125% of the continuous load plus any non-continuous load. They're protected against overcurrent by an overcurrent protection device, and that device is sized to be just larger than 125% of the continuous load. In other words, you take the feeder amperage, you multiply by 25%, and then you round up to the nearest breaker sizing. You got the, okay, so we need some definitions. The ground is the earth, grounding, connected to ground, or a conductive body that extends into the ground. And then you have the equipment grounding conductor. The conductive path installed to connect non-current carrying parts to the system grounded conductor or to the grounding electroconductor, or both. So the EGC is the path to ground that connects all your metal parts, or the system grounded conductor, which we really don't know what that is yet, or the grounding electroconductor to ground, or both. Well, what is this? Well, the grounding electroconductor is different from the equipment ground conductor. The grounding electroconductor is the actual conductor. Here's your ground. And the grounding electroconductor is the actual conductor that connects your system to ground. And so why would the EGC connect the grounding electrode conductor to ground? That's confusing. Like the grounding electrode conductor is connected to ground. So this equipment ground conductor that is not directly connected to ground, but just takes all these metal current carrying parts to ground. Well, technically, this part of the grounding electroconductor is also the EGC path. And on top of that, you might have a circumstance where you have a DC side and an AC side, and that DC side, the ground might be connected up in the same spot. They might share it. So you might have a DC grounding electrode conductor that's being carried through the AC equipment ground conductor. And so when you're sizing your grounding system, you have to think, well, is this the only connection of my DC system to ground? What's that wire size? If you're combining your DC and your AC grounding systems, being that you're at a higher voltage on your DC side, or a different voltage and different amperage on your DC side than on your AC side, it may come that your DC side requires a larger cable. Like if you're doing a DC system or an AC three-phase system, it may be that your DC grounding requirements require a thicker cable than AC does. And so sometimes your path to ground can be subject to special grounding electrode conductor rules, or your equipment grounding conductor is not really doing anything more than saying, well, you have metal parts on your system, like the frame of your solar modules. They're not intended to be energized, but they're around all this electricity. And so how do we prevent ourselves from touching a metal box or a metal module frame and not electrocuting ourselves? Well, that shouldn't happen if there's nothing going wrong with the system. But what if something goes wrong with the system? That's when we have to be concerned, and we don't want to kill ourselves trying to figure out that there's a problem. We have to connect all the non-current carrying metal parts to ground. Now that starts to be, how strict is that? We say connect all the non-current carrying metal parts to ground, because I have metal module frames, metal racking, my roof might be metal, I have conduit going into metal. I also have little fittings that go onto the conduit that are metal, and then I have little lock rings that when I put the conduit into a box and I want to screw the conduit down onto the box, and the lock ring might be a little metal, and then a washer or a screw is metal. So really, do all metal parts need to be connected to ground? The answer is yeah. There's a ground path for all metal parts on your system to connect to ground. And so what we see in our one-line diagram here is that we have an equipment grounding conductor that is supposed to be connected up to all of your module frames, and we have a metal microinverter. And sometimes it's confusing because your microinverter may be listed as an ungrounded inverter, but it might have a metal frame. And so you say, well, it says ungrounded inverter, but it's a metal frame, so I'm required to connect it to ground. So am I grounding an ungrounded inverter? And that's a little bit of ambiguity that's not supposed to be in code, and it's been clarified in 2017. But yeah, all metal parts need to be connected to ground. So what happens if I have a plastic box instead of a metal box? Well, the plastic doesn't need to be connected to ground, but you still have to carry that grounded connection through the box. And so it's whether or not, how do you get there? Do I connect to, you know, the side of the box and carry that connection through the side of the box? Well, you can only do that with a metal box and not a plastic box. And so then you get into the fittings that go into that box on, you know, do I need to use a grounded fitting that grounds to a ground bar across the plastic box and then ground the next fitting onto that ground bar to carry the cross? Or do I just use a metal box and have the fitting be listed to ground directly to the metal box? Now, you also have an issue where when you get into these metal boxes, you have little knockout holes. And sometimes you have concentric knockout holes that have little dimples built into them so that you could put in 1/2-inch conduit, 3/4-inch conduit, or 1-inch conduit. And I only learned recently that if you put, you use these concentric knockout holes and you put your metal conduit into the smallest hole rather than the largest hole, that because this metal frame is dimpled for these concentric knockouts, that violates the ground path. And so if you're using a concentric knockout ring, you might have to have a fitting that connects to the ground bar. Whereas if you just go and use the concentric knockout that isn't, you know, that isn't there, or just use the outer diameter, you might not need to ground that fitting because it's listed to be grounded already. You know what that means as a designer is a good starting point to set your conduit sizes, as you might want to look at your boxes and say, okay, well, it's designed to take, you know, 3/4-inch or 1-inch conduit. You know, maybe my calculations only say I need to do 3/4-inch, but I'm going to do 1-inch because it's just going to make all these grounding issues, you know, less complicated for my electrician in the field. So anyway, going to your, if you're not familiar with grounding, rely on your general contractor. You know, they're usually afraid of making mistakes and understand this grounding theory better because of their field experience. We got the grounding electrode, a grounding object that has a direct connection to earth. So your grounding electrode is like your ground rod or your ground plate. Your grounding electrode conductor is the physical wire that connects your grounding system to the grounding electrode. And often that physical wire is larger than the rest of your grounding system because it's like the drain, the final drain. And it has to accommodate the ground faults of your entire system and not just one little piece. You got service conductors that go from the point of service to the service of disconnecting needs. So a feeder circuit can be a service conductor. Feeder circuit could also not be a service conductor. It could be an on-site feeder circuit. The service point, the point of connection between the facility serving the utility and your premise wiring. So looking at the system, what's the ground, what's the equipment ground conductor, what's the grounding electrode, what's the grounding electrode conductor, and then we also have the system grounding conductor, the service conductors, and the service point. So the ground is the earth. The equipment ground conductor is the conductor that connects all metal parts to ground. The grounding electrode is this actual ground rod or ground plate. The grounding electrode conductor is this part of the equipment ground conductor system that's a little bit thicker. It's your last stop to ground. We haven't talked about the grounded system conductor yet, and it's very confusing. The grounded system conductor is your neutral wire. And so you might say, well, does that mean the neutral is connected to ground? And the answer is yes, it is. Your neutral is connected to ground. But if you just go into your power outlet and you physically connect the neutral to ground, you might cause a fault in your system, or nothing might happen. It kind of depends on the setting of your neutral. So there's special rules regarding when you connect the neutral to ground, and as kind of the rule of thumb, the neutral to ground should only be connected at one point. And if you are already connected to your utility, usually that neutral to ground connection is made in this meter can, where the neutral may go all the way up, and then they bond the neutral to ground here. So it's a reference point. You know, that means in your neutral, you might have some power going, and eventually it goes all the way down into your grounding system. But it may not have that voltage when it's at a different point on it. And eventually we'll see that the neutral and ground voltage difference helps our breakers function. So we got feeders. Feeders shall not be derived from transformers unless the system has supplied a grounded conductor that is electrically connected to the transformer's grounded conductor. And so what that means is you might have a transformer on a system. You might have a generator or a battery inverter supplying a system. And you also might have a utility supplying a system. And so they both have these neutral conductors, and the neutral conductor has to be connected to ground. And so you might think, well, do I have a separate ground for my generator than I do for my utility? If they're not going to be separately derived, if they're going to be on the same circuit, there should only be one connection point to ground. Bad things happen when you have multiple neutral connection points to ground. You want one reference point for the entire system. Now, it's possible to completely disconnect from the utility and disconnect the neutral to the utility. And at that point, you'll need to establish your own neutral connection to ground. So there's a little bit difference for grid interactive systems than if you're going completely off grid. You know, there's also issues where if you're being required in an off-grid system or a new construction system to install this ground, you know, it might be that even though you put in a ground rod, you don't get the right amount of resistance to ground, and your ground is supposed to be functioning to carry current to ground, but it doesn't have the resistance there. So we get this all the time in Mississippi. In Mississippi, we have it used to be the bottom of an ocean floor, and so very high pressure, just about 2 or 3 feet of sediment, and as soon as you get through that sediment, you get hard concrete rock shelf. And so you take a ground rod and you put it into the ground, and it's an 8-foot ground rod, and it only goes in about 3 feet. And so then per code, you're allowed to tilt that ground rod at 45 degrees, and then it only goes in 4 feet. And there's not enough resistance in that to ground. And furthermore, you know, this mud sediment layer is so thick that it doesn't get very good resistance too. And eventually what you have to do is hollow out whatever ground you can and lay that ground rod flat in the ground and bury it. Well, it still might not give you the resistance you need, you know, so you might have to install multiple ground rods up to the point where you get the resistance that you need. You might be called in National Electric Code to install additional ground rods. So we'll get to that when we get to that section. It's not uncommon to have transformers on a solar array. Generally with the solar array, you're just connecting the neutral of your solar array to the grid connected neutral, because that ground connection of neutral has already been made somewhere else. if you just think, well, the neutral has to be connected to ground and I'm installing the solar array, so somewhere along the line I have to install a ground rod and connect to ground. Just keep in mind your building electrical service already has the neutral connected to ground at some point. So here's what a one-line diagram might look like, where we have a neutral that is being shared between a generator and a battery inverter and a solar inverter and the building neutral. There's no disconnect switch right here on that neutral line, and you have one grounding reference point. Or if you had a complete switch where you are disconnecting from the grid entirely, then at that point you have to think about, well, maybe this grounded connection should be located here instead. Or you're going to have to put an additional switch where that neutral, the new neutral to ground connection is being made at the same time that the old neutral to ground connection is being disconnected. So if you're installing a generator and you're putting in a ground rod right next to the generator and you're bonding the neutral to ground on that generator, then you need to make sure that your neutral to ground reference from the utility side is completely opening up when it comes time for your transfer switch. Otherwise, you just share it. Conductors, minimum ampacity and size. So branch circuits that are not much more than 600 volts apply to table 31015 for sizing, or special conditions for motor circuits. So we're just going to keep moving on into that. And then we see some repetition. We're looking at this feeder on this smart former, and it's, one thing you want to make sure is that your nominal voltages, your kind of electric service matches the, what you think you get. If you want a split phase service, that's going to look different than just a 120 volt service or just a 240 volt service. With commercial services, there's different ways that the wirings inside these transformers work. And so depending on what transformer you're hanging on the wire, you might have a 208Y service, a 480Y service, a 480 delta service. There's different kinds of electrical services that can be hung in. And while to some extent these electrical services are arbitrary, it's what is the nickname, what does your utility like to install? What transformer do they like to buy? What transformer do they like to hang? And maybe there's specialized equipment that just has been historically made for a certain kind of electric service, and so you need a certain kind of transformer. Generally, they all revolve around common nicknames within a jurisdiction, at least. And so here's how, we have our higher voltage power lines coming in from the utility. So we have a distribution circuit that may be at a 2,400 volts, and then we hang a transformer onto the line, and coming out of the transformer itself is our 240 volt split phase electric service. And that's pretty typical for US residential. Some of the stuff on the utility pole, eventually, if you're a solar designer, it's like, okay, I get the specifying the circuits to the inverter, that's string sizing, and I can do my racking design in my racking configurator, and I can do my performance estimates and sell the system. So I'm just going to do high level array layouts and bill of materials, specialty material specification, and I'm going to let the contractor do everything else. And that's fine. But once you want to get into off-grid design, tiny house design, or just take on more mainstream electrical scopes, so you have more stuff to do, Then you're specifying your meter box. Often the utility will want you to provide the meter box, but it needs to be a special type so that it fits with their particular meter. That requires coordination at the local level. If you have a overhead wire run, the same issues with leaks and moisture. The utility doesn't want moisture getting into their meter, and so what might look a little ugly to someone. Why are these power lines just dangling off of the here, and it looks like there's a lot of slack in them that's going into here? Well, this is called a drip loop, and so it's water can drip off the cable rather than running directly into the cable. And that applies on a rooftop too. A rooftop is a sloped surface. If let's say you have a choice of putting your junction box here or your junction box here for going into the rooftop. If you come up to the top of the roof, you're going to have less water running down it. If you go into the bottom, water is going to be running in this direction. What you certainly don't want to do is enter into this box at the top here, because water is going to be running into that fitting and trying to get in there. You want to come around the box on the bottom side and go in through the bottom. So all of a sudden on a past picture, we have way back. Yeah, now we see this box. It's located kind of towards the top of the roof, and we're coming in through the bottom of it, for the same reason that you have these loose conductors coming off from the utility transformer into the home, to avoid rainwater runoff. But it's usually this stuff like what meter box does the utility want? Are we going to go in a overhead or underground service entrance? Requires some local customization. Looking at this stuff, we have our high voltage line coming in from the utility, and they're still doing a neutral reference into this transformer. They have a little fuse. When it comes time to do commissioning, they may poke that fuse and unlatch it with a pole to simulate a grid failure. And then we see this ground being made to provide a neutral reference to ground here at the transformer. So the transformer knows if there's something going wrong. If you really blow a circuit, you might trip this fuse up in the utility transformer, and that's when the power company may need to come back out to reset your electric service, as if you've done something real wrong. So the neutral conductor, the conductor connected to the neutral point of a system that is intended to carry current under normal circumstances. So the neutral conductor, it's called neutral, but it is intended to carry current. It's not like the equipment ground conductor, which is just connecting all the metal bits together, and any current on any point of the system is immediately shuttled away to ground. The neutral is intended to carry current under normal conditions. Without getting too far into the theory, when you have a 240 volt service coming in from the utility, the neutral kind of functions as a seesaw, recirculating the voltage difference. If you have a different load on leg 1 and a different load on leg 2, your voltage levels in your different legs will be slightly different from each other. And that's going to cause power to recirculate back through the neutral. And that recirculation can be as great as if one leg has absolutely no load on it and the other leg is fully loaded up. And what that means is that neutral wire is being used to recirculate your system voltage, and the amount of voltage in that wire is as great as if one branch circuit has no continuous load on it and the other branch circuit has a continuous load and a non-continuous load. Well, what's the size of your neutral need to be? it needs to be the same size as your other circuits. It needs to be sized to carry all of the current from one circuit all the way back home. Well, maybe or maybe not. If one circuit and another circuit both have load on it at all times, maybe it only needs to be sized to carry the difference between the two back. And so you get into the concept of, under some circumstances, you can have an undersized neutral, and under circumstances you can't. You know, on a solar array, there's really no reason to have a undersized neutral. You know, if you have a fault from one feeder circuit and that's completely off, you know, there you can imagine a number of circumstances where one circuit is off and the other's on. So normally with solar, you're not going to have an undersized neutral. You want to just keep the neutral the same size as a starting point, unless you can find a reference in code to undersize it. Also, in commercial, you get different transformer wiring. So this is a delta wiring versus a Y configuration wiring. And the important takeaway is that they are, in fact, different. If you have a three-phase Y configuration inverter, it's not going to work on a three-phase delta configuration, even if you are told that they have the same voltages. When I'm making my warning labels and placards, you know, one thing you might ask yourself is, well, how far out do I need to extend my calculations when submitting permitting plans? Do they want to see that I'm an engineer and so I know how to do significant digits, and if I can carry everything out to 5 significant digits, should I? Or what? Or do I opt for something that is a little bit dumber? You know, I might have to round up for safety, or do I have to round up for safety? You know, are they looking for 240, 241, 242, or just 240, 245? Yeah, I'm rounding up for breaker sizes, so how do I round my calculations? Well, here it's actually defined in National Electric Code. Yeah, the calculations are permitted to be rounded down to the nearest amp. And then then code trips on itself again and says with decimal fractions smaller than 0.5 dropped. And don't confuse yourself. You're allowed to round down to the nearest whole number when doing your calculations. Now, I like to carry the significant digits all the way through to the end and then round down. But that's, you know, you're allowed to round down to the nearest whole number. You don't have to get into fractions of an amp or fractions of a volt. You can, and in fact, if you go through a professional engineering process, professional electrical engineers can calculate the actual voltage and actual amperage and design around that, rather than using the tables and charts and ASHRAE temperature databases for your voltage correction and going by charts and rules of thumb. You can get down into the exact numbers. That's what a professional engineer does. You know, you might get a professional engineering stamp even if you're not, you know, trying to optimize your calculations. Usually optimization at that level is going to cause you more grief than anything else. Okay, getting into branch circuit calculations, we have lighting for specified occupancies, other loads. So we have dryers and cooking equipment, motor loads, light fixtures, outlets, dwelling units versus non-dwelling units. You know, code has rules for all these specific appliances. You know, air conditioners, refrigerators. Haven't really seen washing machines yet. The minimum load of a feeder or service is the sum of the loads determined by Part 2 after any demand factors permitted by 3, 4, or 5 come into effect. And so what we have is for every kind of appliance, You know, like with electric dryers and electric cooking, there may be some additional factors put into your calculation. I mean, one thing that's always strange is you look at your service panel, and it's a 200 amp panel, and you might have 300 or 400 amps of circuits on that panel, and you think, well, how the heck does this work if I have 200 amp service but I have 400 amps of breakers? You know, what's going to happen if, you know, what that seems like if I turned on all of my appliances at once, I would trip the main breaker of my house. And I suppose you could do that. It would be kind of hard because of all these other safety factors that are built into it. Yeah, there's custom calculations designed for things like a electric range stove, where the circuit has to be sized as if the stove had all 4 burners or 6 burners on 10 out of 10 hot rating plus the oven on. But that doesn't mean that in terms of sizing the power supplied into the building, that you have to assume that all the devices in the building are on at once. But then again, there are minimum, you know, it's like 100 amp electric service is the minimum service size. So even if you are trying to do a tiny house, and you might think, well, I'm going to force the customer to only live on 20 amps of power, there's minimum service requirements in code as well. So then we get into the authority having jurisdiction. An organization, office, or individual responsible for enforcing code. You know, if you're unfamiliar with your authority on who you contact when developing a project, you can always go to the Desire website, look up your interconnection standards, and it'll refer you to the you know, major investor-owned utilities contact information and your state public utility. And looking at some of these exceptions, fixed electric space heating, rather than being calculated at 100%, if you're managing your own energy, the AHJ can allow the feeder and service conductors to have less than 100%, provided that the conductors have an ampacity for the load so determined. So, you know, if you are doing electric space heating versus running an air condition, you're probably not doing the same at the same time. And so there are certain scenarios where your AHJ is the final determination on what you do. And there are economies of scale that when you get into multi-tenant dwellings, you know, you don't have to assume it's like a single tenant dwelling where you have one stovetop. Not everyone cooks their dinner at the same time, and so you get discount factors as you scale up. The feeder or service neutral, the maximum unbalanced load is the maximum net load between the neutral conductor and any one ungrounded conductor, and then you get into being able to reduce the neutral. So starting out, it's not that you start out with an undersized neutral and then for some reason you have to step up. You're never going to make a mistake if you start with a full-size neutral and then step down. It's just that you might find a cable assembly that is only used under normal circumstances that allow you to step down a neutral. So, you know, for our designs, let's just keep the neutral full size for now to avoid making a mistake. You get a couple of different ways to calculate loads in code. You may calculate lighting loads by the square foot. You might be given just some general rules of thumb for your branch circuits. Your appliances, your dryers, water heaters, cooking equipment are all factored into your general loads. And then you get case uses for air conditioning and heating loads, since they're assuming it's not going to be on at the same time. So when you're kind of determining if you're doing a microgrid design, You want to determine the smallest electric service. This is why we get into the point where, the builders will just put in a 200 amp service, even though one particular customer, you look at their power draw and it's like, well, their electric service can go all the way up to 50 kilowatts, but they're never getting above 4 kilowatts. So why are we giving them a 200 amp service instead of a 100 amp service? Well, it's just easier to by the time you get into code is not looking at all of your on-site optimization. It's trying to set a minimum rule of thumb. Different rules for different kinds of units, like schools, restaurants, farming, multifamily housing. You're allowed to set the size of your electric service based off data that you've monitored from the site. So if you want to downgrade your service or upgrade your service, you can use actually measured data if you have a 1 year period. If you don't have a 1 year period, you can base your service data off the maximum 15 minutes of demand using the highest heating or cooling load conditions over 30 days. And so where I've seen this kind of come into play for solar is you might have a utility coming in and saying, well, to net meter your array, we're going to look at the maximum load your home has drawn over the last 12 months. And, I've had one client where he said, well, the utility only, told me that I could only do a 10 kilowatt array, and he wanted to do a 50 kilowatt array based off the economics in his area for backfeeding the grid. And so what he did is he went around to every appliance in his house and he turned it on and ran his panel all the way up to its maximum, 48 kilowatt capacity for 15 minutes. And that, showed the utility that, yes, his home, he might not be using all of its power. They're calculating it based off his existing power usage. So he went and showed them that, he could actually be drawing more power if he wanted to. The definition of a building, a structure that stands alone or that is cut off from an adjoining structure by firewalls with all openings protected by approved fire doors. A garage is a building or a portion of a building where vehicles are kept. So a garage is a building. There's certain rules that apply to buildings, and garages constitute buildings. Bonding, connected to establish electrical continuity and conductivity. So bonding and grounding are essentially the same thing, although I guess technically you could be bonded and not connected to ground. The bonding jumper system is the connection between grounded circuit conductors and the supply side bonding jumper or the equipment ground conductor, or both, at a separately derived system. What this means is your bonding jumper is where the neutral and the supply side bonding jumper or the equipment ground conductor are connected. Or it could be the connection between just get to that a little bit different. One thing you need to know about bonding is all of your metal parts need to be connected. And so while that might be managed by a grounding terminal inside a box, when you get into your solar rail, normally you're going to get clips that ground the module frames directly to your module rail. So you normally have this grounded connection between your module rails. But then you get to this point where you take your metal and your other piece of metal and you install a splice bar between the two. Or you take a metal pier and you drive it into the ground, and then you put a metal racking on top of that. And you say, okay, well, I know when I use these specialized grounding washers, I am etching into the module frame and biting into the module frame. And so even if I have an anodized coating that can impact my connectivity, these grounding washers help me get through that so that everything's grounded together. But what about if I have a pile that's going driven directly into the ground? Is that a grounded connection? Or if I take a stick of metal and another stick of metal and I just touch them together, is that a bonded connection? And the answer is, well, it depends. And it really depends on if it's listed for that. And let's see, I got a question here. Let me see if I can make it any larger. Let's see, do you still use the Dropbox? Are the presentations there? So on the code distribution, I'm kind of wary of using the Dropbox because I'm not supposed to distribute physical copies of code. Really what I'm using for content distribution is my website. So if you just send me an email, I'll get you set up with the course recordings. And it's a good one to do on this program in particular because it's our newest program. So we are in a constant state of revision and updating on it. So what you have in the solar industry here is what's called a bonding jumper, that even though we have two sticks of metal rail and a splice, and it's a metal splice, it may not be listed as a bond path. And so we have an additional bonding jumper that is our listed path. You might have a metal pile going into the ground. It may not be listed as a ground path. And there are certain rules on if the metal is large enough, then it doesn't need to be. It is listed. But it might be that the metal pile is so small or that it has an anodized coating on it, so it just doesn't get the resistance that it needs to actually be a ground path. So you should not assume that things are grounded simply because you have a metal on metal connection. It may not be grounded enough is the issue. That's why we use solar racking systems, and that's really kind of the difference between a metal roof and a homemade racking system versus using a solar manufactured racking system. Is if you're homemaking your racking system, you still have to use a grounded listed grounding method. And if your metal rail is not listed as a ground path, instead of grounding the modules to the rail, you have to ground the modules to each other, and just you still have to ground the rail, but it's not listed as a ground path from the modules through the rail to the grounding system. And it used to be in old school solar design, you would actually run copper throughout the entire array and connect every single module onto the copper conductor because the rails were not listed as a ground path. Now the rails are listed as a ground path, but you have to use a specialized little jumper to ground your rail-to-rail connection. So where's the bonding jumper of the system? The bonding jumper that connects the neutral path to ground, it's commonly in the utility meter itself, so it can be kind of hidden. In fact, on our off-grid system, we got to the end, the electrician got to the end of it, and he says, well, I don't understand kind of how the neutral is supposed to work, because normally the neutral is going to be connected to ground at the utility meter, and now we're off grid. We don't have a utility meter, and so we had to install our own bonding jumper to connect that neutral to ground. A substation, an enclosed assemblage of equipment, switches, circuit breakers, buses, and transformers under the control of qualified persons through which electric energy is passed for the purposes of switching or modifying its characteristics. So every so often, as you climb down that mountain from high voltage to low voltage, you get to a substation that either is going to step that voltage back up so that it can be transmitted over an even longer distance, or it's going to step that voltage down so that it can safely come into your building distribution circuit. We have rules for branch circuits that are outside rather than inside. You know, different rules for if they're on building structures and poles and otherwise. So we have a table that catalogs these rules for different kinds of outdoor equipment. So, you know, there are specific code rules for floating buildings. So if you wanted to get into like floating solar, table 225.3 is like the real table of contents to your specialized outdoor equipment circuits. And let's define a raceway. A raceway is an exposed channel of metal or non-metal, so like PVC, designed for holding wires, cables, or bus bars together. And then we have the enclosed, where it's surrounded by a case, a housing, a fence, or a wall that prevents persons from accidentally contacting energized parts. And what's interesting about solar raceways is raceways, you can have an enclosed requirement, you know, or you might not have an enclosed requirement. So you might have a stick of unistrut that has little washers built in, but it has a U channel in it, and that could be a raceway to kind of support your wiring, for holding wiring, but it's not an enclosed raceway. You know, it might be that your solar cables should not go into an enclosed raceway because they need this airflow in them. So if you have a cable tray with solar conductors, it may be a ladder tray if you're up on the rooftop and you're using your high voltage solar cable, so that you still have airflow into it. But when you go inside of a building, you may have a different set of requirements. When you're inside a building, your DC conductors must be fully enclosed. And so what might work as a raceway up on top of a roof may not work inside of a building. Ground fault, an unintentional electrical connection between an ungrounded conductor and a normal non-carrying part. So that could be, and then you have a ground fault circuit interrupter, a device intended to protect persons in the event of a ground fault. Let's just keep going. Well, now we have a different kind of fault, an arc fault. So a device intended to provide protection from the effects of arc faults. And so we have an arc fault current interrupter versus a ground fault current interrupter. And a ground fault is when you take a energized power line. So here's your solar MC4 connector. Let's say that connector is not made up tight and you have a fault here. Or let's say you have this cable is inside some conduit on a fixed rigid metal, and that thermal expansion is causing that metal to pull apart, and all of a sudden this cable breaks and it's faulting into the metal, you know, and that metal is connected to ground, and so that fault is clearing into ground. You know, that's a ground fault. Arc faults are different. Arc faults are, you know, you have a cable, and let's say that cable gets pulled apart, and so now you have a broken cable, but it's sitting in plastic PVC conduit. And so now there's no path to ground, but you have a faulted cable, and so you get little sparks that go across that connection. You know, maybe it's connected and you get full current, and then it changes, and the resistance goes way up, and it starts to heat up, and it heats up this PVC and melts it onto the rooftop and starts burning your roof and starts burning your building down. that's different than a ground fault, and it's detected differently than a ground fault. Arc faults might be resistance in the cable, jumping up and down. Whereas ground fault, you might be simply monitoring the neutral wire or the ground wire, and if there's a difference in voltage between your neutral and ground, that gets large enough, it might trigger your ground fault. If it doesn't get large enough, you still might have a ground fault. It's just not enough to worry about. It might be that you have wires pulling apart in an arc fault, but it's not arcing into your metal conduit, and you might have an arc fault that's not a ground fault. And I can tell you, arc fault is usually a workmanship issue. Ground faulting was more of a concern. It becomes a concern when you have multiple cables and parallel to each other. So when you have one cable and you have an overcurrent protection fuse, there's really not much danger there because your power going in across the fuse is the same as your power going out. When you have two cables coming in, it's kind of the same way, because if there's something that's going wrong here, this cable is designed for the full current of one circuit, and so then there's safety provisions put into that. When you get into 3 or more circuits being wired in parallel to each other and you get into fault conditions, the concern is, while this home run cable may be sized to accommodate all of the current from your application, if your more powerful circuit starts backfeeding the smaller circuit as that power tries to find a path to ground, let's say there's a problem here, these smaller conductors could get more ampacity than what they're designed for and burn up and melt. And depending on how that fault occurs, if it doesn't occur all at once, but what might happen is that one module fails and it backflows into one current, and it's not enough to trigger any alarms. But it's failing because this box is being pulled apart by thermal expansion, and all of a sudden we have a situation where we have cascading failures that are slowly elevating not just our neutral voltage, but also our ground reference, and it's not triggering the ground fault detection. And so we've had an instance where the way that traditional inverters were monitoring ground fault detection has a blind spot in it. And this is for what are called grounded inverters that are connecting their negative DC circuit to ground. They have a blind spot where small failures can elevate that grounded circuit, and if your ground is raising in voltage and your ground fault detection is monitoring the difference between your negative circuit and ground, it could cause a blind spot. And so they've in newer inverters, they're called ungrounded inverters, and they've taken out that negatively grounded point of reference in the DC ground fault protection circuit and kind of resolved that blind spot issue. But the takeaway is, whenever you have multiple circuits in parallel with each other, there's more safety concerns than when it's just 1 or 2 circuits. So when you have multiple circuits in parallel with each other, that's when you start having to fuse each circuit. If you just have 2 circuits being combined, they are not required to be fused. Now, arc fault currents are harder to detect. And it used to be that in the solar design, we just didn't detect them. because they're more difficult and expensive to detect, and the arc fault detection circuit technology was not developed for the solar industry. But I can tell you where a common arc fault is in the MC4 connector housing. So here's our housing for our solar cable. So this is from the solar array going into this housing. And inside this housing, there's a crimp. And the crimp sheathing goes around the conductor, and you kind of strip out the jacket. So there's a thicker cable jacket, and you strip it out so that just the copper is exposed. And then you crimp on a connector to it, and then you take your other solar connector that has the same thing with a little crimped connection, and they plug into each other, module to module to module. It's called an MC4 connector. And when you get into the solar brass tacks, there are, even though MC4 is a standard, there are different MC4 connectors out there, and while they're all compatible with each other, the difference is, is this little crimped metal piece that forms the actual thing that's getting plugged into each other, does it go completely around? Like, is it a circle that goes on and is crimped on all ends, or is it a U channel that might slip? And then there's in addition to that, there's a little nut at the bottom of this connector that's used to tighten up this. And so it's a little messy up on screen, I know that. But with MC4 connectors, there's a couple of different ways they can fail. One is the crimp is not made tight enough and it slips. The other is that the cable itself is not made tight enough with this little nut, and that slips, and it creates this little spark between your two wires of this arc fault. Now, it might be that is just a little bit of arcing, and most of it is a continuous connection. And your older inverters that did not do arc fault detection, you would still get current across it. They weren't detecting the arc fault, so there was an error, but it wasn't reading it, and that gave solar almost a feeling of being bulletproof, because you get all these amateur installers out there making bad connections, but it doesn't really impact system performance upon commissioning. It's not a big problem yet. It's not impacting your performance. The inverter doesn't see the error, and so you say, well, solar has no errors and it's super easy. Well, now your newer inverters have this arc fault detection, and upon commissioning, lo and behold, usually if you're using an amateur crew, you're going to have to go back and fix an MC4 connector or two to make sure it's tight. So there's different kinds of faults on a job site, and the arc fault is different from a ground fault. Also, that's when you get your combiner boxes. The reason why we have these fused circuits coming into a bus bar is the same reason why in your service panel you have breakers on all the individual circuits. Whenever you're wiring 3 or more circuits together, you have to have an inline fuse or an inline breaker. Is a ground fault GFCI the same as a ground fault circuit interrupter? Yes. So there's different ways to reduce ground faults versus arc faults. One area where ground faults are very common are longer circuits. So when you do long circuits on a rooftop with long circuits of rail, you might forget to use expansion fittings. And if you don't use those expansion fittings, the rail might pull apart. Well, still, your conductors are not going to be expanding the same as your rail. So if you don't put slack in your conductors, you could be pulling, your rail may be expanding, but your conductors may not be. You could be pulling your your rail apart and they fault onto those metal conductors. So if you use little shorter array blocks, and we're talking about, this is more a commercial design issue. Generally, in fire code, we see that every 150 feet you need to put an 8-foot walkway. And you might say, well, that's ridiculous. I want to fill up the entire rooftop. Well, you also might have, that might be there not just for rooftop access. It might be, what it is about every 120 feet you need an expansion fitting, or you can just use smaller array blocks and not have thermal expansion be so much of an issue. For reducing arc faults, that's more of a workmanship issue where you want to make sure every electrical connection is being made up tight. Back to wiring on buildings. Building wiring goes up to 600 volts. For using, you're allowed to use different cables. And so you're allowed to use MC cable, MI cable, put it in metal conduit. And so you might be finding yourself doing a solar circuit and saying, well, I'm inside a building. I need to be in an enclosed metal raceway, or I need to be enclosed in metal. Could I use a metal cable that has a metal cladding around or sheathing around the cable rather than putting it into EMT conduit? Yeah, you can. Let's see. So there's you can say, okay, between my conductors, there's different spacings for less than 600 volts and greater than 600 volts, but there are rules and regulations that refer to distances, support distances, and clearance when you're above a building. And so you might look at the rooftop of a row home, say, well, wouldn't it be great for me to put an outdoor patio or decking here? Well, it depends if you have power lines that are going across the building or not. You might not be able to because of clearance requirements for overhead power lines. So for above rooftops, for systems that are not over 600 volts, generally you have to be 8 feet above the roof, 3 feet in all directions from, say, windows. And if it's a pedestrian rooftop, you may need to go even larger than that. And so really it's, if you want to build a pergola out of solar, going for a 10-foot height of that pergola will keep you in the clear of your inspections. You might want to do a 6-foot height because that's better for your wind loading, but it's a code violation. The only area where you're allowed to put your wires closer to a building or window than 3 feet is if you're up at the top of the building. So here's your building. You have a window, a window, a window, a window. You have to stay 3 feet away, except for the very top where you're allowed to tuck it between the awning and that window in a closer proximity, because you really don't have a choice otherwise. The main thing on your raceways is they need to be arranged to drain. You don't want water tracking down a raceway and getting into your boxes. We talked about the raceway seal. That's a very common exam question. You get in a number of supplies. So if we have our utility supply, our solar supply, a generator supply, a battery supply, how many supplies can we have coming into a building? And the answer is you can only have one supply except special conditions. it makes sense to have an emergency power supply being separate from a standard power supply. You want your smoke alarm batteries and fire alarm batteries or your defibrillators or grandma's insulin medication refrigerator. You want those to not lose power if you have to cut power to the building. So you're allowed to supply a building with multiple supplies under certain conditions: standby, parallel power production systems. Pretty much anything you can imagine that produces power is allowed to be a supply. Not things like, electric vehicle battery that you pulled out of an electric vehicle. And that might be stated again in special conditions. You might be required to put additional feeders, but when you say, well, how large of a supply can I do before my utility is going to say, well, you need to have 2 or 3 services going into the building. You're only supposed to have 1, except for special conditions. But then the utility might say you might have additional services when you start drawing more than 2,000 amps. A home has a 200 amp service panel. Once you get into buildings that have electrical usage that is greater than maybe 10 homes or so, do you get into additional feeders? Disconnecting means whenever you have a supply that goes through a building or a structure, you should have a disconnecting means. It should be installed either inside or outside the building where the conductors pass into the building. No problem with having it both. The disconnecting means shall be readily accessible at the nearest point of entrance to the conductors. And so this concept of readily accessible starts to trip up jurisdictions with regard to the disconnect switch that might go into the building, because you have a rooftop solar array, and then you're going from the roof into the building, and now we have a disconnect switch that needs to, for feeder circuits, that needs to be readily accessible. So where can I put it? Can I put it in the attic? Well, you're allowed to. It says it can be on inside or outside, but it also has to be readily accessible. So the question is that attic space readily accessible? And what's the definition between accessible and readily accessible? So accessible, you have not guarded by locked doors, elevation, or other means. Readily accessible is able to be quickly reached without being able to climb over obstacles or remove obstacles. So, a rooftop is not going to be a readily accessible place. Now, the utility, what they want to see is a shutoff switch for the system, and they don't even really go by readily accessible, which could be inside a doorway inside the building. Most utility jurisdictions go above and beyond this readily accessible requirement by requiring a disconnect switch to be outside the building that can cut power to the system. But that philosophy gets murky when, okay, well, the system, a dumb solar array is listed to automatically shut off during a power failure. And so that switch doesn't really do anything other than provide some additional assurance. But what if the solar array is providing power to an emergency backup system? You don't want to just have a switch there on the outside of the building for anyone to turn off for any reason. You might want to secure the switch. And so then the question becomes, well, with readily accessible, what if you need a key to access the switch? Is it readily accessible or not? And the answer has been yes. You can use a locked box can still house a readily accessible switch. But utilities muddy the waters by saying, no, we want a external knife switch disconnect, and there for our solar array without much kind of reasoning behind it. That's just a common requirement. Now, a generator has the similar design issues as a solar array. And so you get to the point where you have a generator feeding a system, and the generator needs to have a disconnecting means, and the generator needs to be, the disconnect needs to be readily accessible. And that's where you get this insight from distance, where you show up to a building that's on fire and it has a backup power system with a generator. It's readily accessible and apparent to the fire department that that generator is there, and they can walk up to the generator and turn the disconnect switch off and kill power to the building. So you need something similar of that for a solar array. And I had an issue where I had a solar array that was about 50 feet from the home. And so we didn't need to have a disconnect switch out at the solar array. We have a solar array, underground wire run, and then our house. And it's less than 50 feet between the house and the solar array. And the question is, well, do you need a disconnect switch at the solar array? No. Oh, no. It's only if it's greater than 50 feet. Well, we thought we were being smart by saying, okay, so we don't need a disconnect switch. And so we're going to just take the 3 circuits from the solar array ground mount and run them directly into the ground and to do a direct burial run. So all we have to do is rent a trencher, dig the trench, throw the wires into the trench, and cover it back up. And we were trying to get the most bang for our buck and spend money on solar and not on unnecessary equipment. Well, having a switch out at your solar array is a good idea too, just from a servicing standpoint. Where it turns out on this array we turned it on and we had an arc fault connection, and we didn't know where it was in the system. So we had to spend a lot of time kind of marching back and forth between the house and the solar array, manually plugging and unplugging the circuits of the array, which is really not a safe practice for testing, and then walking back to the inverter and reading the screen off the side of the inverter to say, well, did it clear the arc fault? Did it clear the arc fault? Whereas if we had just gone above and beyond code, and even though we didn't have to have an additional disconnect at the array itself, if we had just put that additional disconnect there, it would have made servicing easier. So in short, with all these disconnects, the arrays need to have a disconnect switch. What the utility really wants is a disconnect switch that's outside of the home, that's readily accessible to them, that during an emergency, they can come and turn off power to the entire building. But that's going to get a little more complicated as solar and batteries come onto the scope, because now they'll be used not just for standby systems, but also for emergency systems. And if grandma's is living in the attic on a defibrillator or something where they need to keep her alive on an iron lung, and if they kill power to it, she's going to die. The fire department now, they don't want to. How do they determine the difference between a feeder that's supplying a building and a feeder that's supplying a building during an emergency system, now that the batteries might be located inside the building and the solar array might be on top of the building? How do we make it apparent the difference between your main power supply and your other forms of backup power? And the answer is you put them in different locations. So they're both readily accessible, but if you have a backup system or emergency system, you have to put it physically separated from your mains, so that if you're just turning off all your mains, then you have to walk, and it might just be a distance of 10 feet, but something where you have to have an intentional act to go to a different location to turn off your backup and standby. So now we have multiple services coming into the building, not just for your main power supply, but also your backup and standby supplies. They're allowed to be inside the structure or outside the structure, but often the utility will say no, they want to be outside the structure. You can argue with them that they should be inside the structure because you don't want, just the general public to have a big red button on the side of your building that can turn it all off at once. But the main rule you need to know when determining how many supplies, if you have a generator, a battery bank, maybe a second battery bank, maybe a second generator, large generator and a small generator might have separate purposes on a microgrid. Having a lead acid battery bank and a lithium ion battery bank operating in parallel might have special purposes. So who knows? The rule for determining how many supplies or even how many loads for that matter on a service panel is, if you have more than 6 switches, you need to have a main switch. So if you're designing a utility scale solar farm and you have distributed inverters and you have 7 inverters on a panel, that panel needs a main breaker or disconnect switch. If you only have 6, then 6 is considered what you can do in a short period of time to turn off all the power. 7, that's the cutoff. It's too much. And so you can have 6 inverters going into a transformer. If you have 7, you need to have a main disconnect switch. You could have 14 inverters going into 2 main disconnect switches going into a transformer. You could have 6 different backup power supplies. If you have 7, you need to combine them all into one panel and have one main switch. So for individual separate parts, for your backup power supplies, you can have up to 6 switches before you have a main. For your main power supply, you can have up to 6 switches before you have a main. For your load panels, you can have up to 6 breakers before you have a main. 6 is the magic number in this circumstance. Okay, so we have, well, looking at the time, we're 5 minutes over, and we're still in section 200. But what we're going to do tomorrow in the morning bit is go from section 200 through section 300 in the morning, and then after the break, we'll talk about specific rules and regulations for the solar equipment. So we're still making our way through code. But let's not worry about that for now. We're back here tomorrow, so let's pick up then. Thanks for listening in, and we'll see you guys tomorrow. I'll pass it back to Half Moon.
Great, thanks JR. Thanks everybody in attendance. That concludes today's webinar. When I close things down, everybody will be sent over to a brief quiz. It's not meant to catch anybody up, it's just meant to prove attendance. Once we receive that quiz from you, you'll have your certificates emailed to you in a PDF format within 5 business days. If you need them any sooner for licensing purposes, certainly call into our office, or you can reply back to any of the emails regarding any of the webinars you're attending, and we can help you out there too. That's all I have. Again, thanks JR. See most of you tomorrow.